Hello, thank you so much for watching this video. My name is David Richter. I'm at the University of Notre Dame, and what I'm going to talk about has been a sort of a group effort with a former postdoc of mine, Wang, who's now at the University of Twente, and a friend and collaborator, Andy Bragg, at Duke University. So what we're going to talk about is the settling of inertial particles through wall turbulence. And so, kind of before I get into the details of that, the things that I personally am interested in are multi-phase flows. And I imagine that anyone who is watching this video probably has some sort of interest in this as well. So I won't belabor the point. But for me in particular, I like environmental flows, so things like clouds, sand and dust, snow and that sort of thing. And so, understanding how this is transported in the boundary layer of the atmosphere is actually quite important for a lot of different reasons. Sort of a more technical motivation for what we're studying here is by looking back at some famous results or well-known results in the area of homogeneous isotropic turbulence. And so, I've pulled a few here. This is a study done by Eliseda et al. In 2002. And the idea here is that, with increasing inertia, the average particle velocity, that's this VZ here, actually starts to exceed the Stokes settling velocity that you would expect for a small particle in a quiescent fluid, governed completely by Stokes drag. And so it's a function of the inertia as given by the Stokes number, and people have seen this sort of peak around a Stokes number of 1. And so you actually get this, an average particle velocity which is faster than what it would be in the absence of any of the turbulence or inertial effects. This has been, seen also in DNS by Rosa et al. In 2016. There was a paper by Good et al. In 2014 that did a pretty good job of summarizing a lot of the work in this up to that point. And of course, there's the sort of the famous conceptual picture of Wang and Maxey in '93 of this preferential sweeping mechanism, where the particles, when they have inertia, they're able to sort of get swept to the side, the downward side of vortices as they settle through homogeneous and isotropic turbulence. And so because they preferentially sample downward velocities, you start to get average particle velocities which can exceed their settling velocity. And even within the realm of homogeneous isotropic turbulence, there's still some outstanding questions, like which velocity scale to use in order to see this. And in a related question, do you use the Kolmogorov scale or do you use sort of a large scale velocity? And a related question is, how does this affect scale with Reynolds number? And there's a lot of people trying to work on different aspects of that. What we're doing, though, is actually slightly different. Instead of looking at those two questions, we're saying, well, how does this change, or does it change in wall turbulence as opposed to homogeneous isotropic turbulence, where comparatively very little is known? There's a classic result from Rouse in 1937, which states that in the logarithmic layer, so we're talking outside of any sort of viscous or roughness layer in wall turbulence, a scalar, so that's with concentration C, that has a constant settling velocity. So this is sometimes called like a heavy scalar. So think like dust or pollen in the atmosphere, something that's very small, very inertialess, but settles down with some small but constant settling velocity, exhibits a power law. So the average concentration goes up like Z to some power, and this power is sometimes called the Rouse number. And it's really just a balance of how fast it's settling compared to the turbulence strength as given by the friction velocity. So that's great, and this is actually a quite important result because it relates the flux at any height, which is just given by the settling flux, to the concentration. And so this kind of goes both ways. In a lot of sort of LES or even larger scale, like atmospheric transport models, this sort of relationship is used for setting the boundary condition of these heavy scalars. The reverse is also used a lot, where you might go out and you might make a fixed height measurement of aerosols or dust or something like this over some surface, and then infer what the surface emission was by using this relationship. And so it's actually quite an important relationship. However, it does not account for inertia at all. And so there's a study that myself and Marcelo Cemecchi did a couple years ago where we said, all right, look, I'm not going to get into the details of this, but this red line here is for a Stokes number of 0. That is the Rouse profile. Okay, for fixed settling velocity, if you just simply increase the inertia, you actually see a drastic change in the concentration profile itself. So if you start to add inertia to the system, this relationship right here is violated. And the primary question here is, okay, what is controlling this, and how does the settling rate through wall turbulence actually change, and what controls it? So in order to do this, we're going to just consider a canonical case of turbulent wall-bounded flow, and that's open channel flow at an RE tau of 315. We're going to introduce a theoretical framework for studying this, but we're also going to run some DNS where we just introduce one-way coupled particles, very standard point particle approximation with Stokes numbers based on the viscous scale between 0 and about 50. And like the study I just referred to, we're going to keep, this is the SV number, so this is the settling rate, the Stokes settling velocity, which is a constant divided by the friction velocity. We're going to keep constant throughout all of the simulations. And that's done by changing the value of the gravitational acceleration. And this is done so that any effect that we see is due only to a change in the Stokes number, not because we're simultaneously changing the settling tendency as well. We're going to look at two different configurations. And so we've got this open channel flow. We're going to look at two particle configurations. On the left here, this is where particles are both introduced from the bottom and they are also settling out towards the bottom. So the top, there's a no flux surface, the particles can't get to the top. And what sets up after a substantial amount of time is a a steady concentration profile where the net flux everywhere in the height is 0. We have to introduce some artificial diffusivity that allows the particles to be resuspended from the bottom, which I'll kind of mention when I show the equations of motion. And so these particles are sitting at the bottom, they can bounce around and they can actually be suspended artificially into the flow. And what you get is a system, again, where you have 0 net flux. In contrast to that, we run the same exact turbulent flow. So the flow is identical because they're one-way coupled. But here we introduce particles at the top. They settle down towards the bottom. When a particle reaches the bottom, it's removed and added to a random location at the top with a velocity equal to its settling velocity. So here we have a non-zero net flux. And so there's a net flux of particles from the top to the bottom on average after you've reached a statistically steady state. Just to sort of foreshadow some of the results, if you take these two and we just simply look at this quantity of interest, and so throughout the entire thing, this is what we actually want to talk about, or at least that I'm going to focus on in this talk here, which is the average settling velocity. In the case of 0 net flux, not surprisingly, the different lines are for different Stokes numbers in this range. In the interior of the channel, the average particle velocity needs to be 0 because we're maintaining a 0 net flux. Down towards the bottom, this isn't true because we have this artificial diffusivity, which I'll mention in just a second. If we look at the non-zero net flux case, we actually see something not too dissimilar from the homogeneous isotropic. In this range of Stokes numbers, as we increase it, we actually get to see an average particle settling velocity, which starts to exceed the settling velocity, the Stokes settling velocity, WS. And so, that's what we've normalized these by. And so, we're seeing up to 10 times for the largest Stokes number, up to velocities, up to 10 times the Stokes velocity. One thing I'll point out here, which is kind of one of the interesting results of this study, is that, if some people just take the SV number, which is the settling velocity related to a flow time scale, and they say, oh, it's very low, so therefore we don't have to worry about this enhancement effect. One thing to keep in mind is that if you normalize by the settling velocity itself, that's probably the more appropriate scale because it shows that, despite it being fairly small compared to the flow time scales, velocity scales, you're actually seeing a significant enhancement over its own Stokes rate. Okay, so as I said, that was sort of foreshadowing some of the DNS. What I want to do is sort of set a theoretical formulation which will allow us to sort of investigate which mechanisms actually control this quantity here, this average settling rate through the flow. So if we just look at the equations governing particle motion, they're very straightforward. Again, if you're watching this video, you're probably familiar with them. The change, the position is due to the particle velocity. And then again, for the case of 0 flux, we have this diffusion, which it's completely artificial and it's used just to make sure that particles are resuspended from the bottom. It's really only not, it's negligible anywhere except close to the bottom wall. The velocity is controlled by momentum conservation. This is just Stokes drag. You can add a drag correction if we apply it. We don't here. This is the fluid velocity at the particle location, and then we can apply wall normal gravity here. What we do for our theoretical formulation is we cast this in phase space. And so we say we're going to describe the particle field as a probability density function in terms of the particle location and velocity and time. And so what you can do is you can create a governing equation for this PDF, which I'm not showing here, and take its moments. And so the 0th moment is actually going to end up in a differential equation for the marginal PDF, which we're calling this rho here, which is basically the concentration. It's proportional to the concentration. If you take the first moment of the equation governing the PDF, you end up with something which is governing the momentum of the dispersed phase, right? Or telling you something about the particle velocity. The details of how you get this equation and then take their moments, you can look in Bragg et al. In 2015. So what's the point? So if we actually go to these equations, these are still exact equations. They're unclosed, but they're exact. If you simplify them for the case that we're studying here, i.e. steady and horizontally homogeneous, we're looking for, what we're interested in is the mean particle velocity, which, this is the equation governing it, but this goes away in steady, and we can try to isolate this term over here. So if we simplify and solve, the first equation for the 0th moment looks something like this. So this phi here is an integration constant, which actually tells us something, or it represents the net flux. Obviously, in the zero flux case, this is 0, and you're left with only something that has to do with the diffusivity, which, again, you have to have in order to actually have a non-trivial solution. For the case of the the non-zero net flux, this is the net flux and this is 0, in which case the concentration is actually algebraically related to the flux and the average particle settling velocity. If you then take the first moment equation, so we're talking this equation down here, you simplify it and you rearrange for this term over here, you get an equation with several terms, and I'll go through them each one at a time. And these are the terms that we're going to investigate for the remainder of the talk. The first term looks like this, and it's an acceleration term due to gradients in the particle velocity. Okay, so it's kind of odd defining the particle velocity based on itself, but this is gradients of the particle velocity leading to an acceleration. The next term is the diffusive flux resulting from a combination of inertia and turbulence. So sometimes this gets lumped into the effect of turbophoresis, but really what this is the tendency of particles to stray from streamlines in the presence of a gradient of the concentration leads to a diffusive-like behavior, okay, which leads to a contribution to this. The next term is from turbophoresis. This term S here is the unclosed Reynolds stress of the particle velocity. So this is the second moment of the particle fluctuating velocity. So gradients of that lead to a turbophoretic drift, which many others have characterized. We have this term here. This is the average velocity seen by the particle, or the average fluid velocity seen by the particle. So this is representing the preferential sampling of the fluid velocity. This is where something like that preferential sweeping effect would be represented. We have our Stokes settling velocity, and then we have a term due to this artificial flux, which I won't say much about because we'll show in just a minute that it's negligible. If I just remind us of what we're looking at, I'm just only going to focus on these two. This is the average particle velocity for the case of zero flux. Here it is for the case of the non-zero. We would like to see what, of these 6 terms that I've just identified, what are important for actually establishing these patterns here. This one's obviously interesting because it changes with Stokes number as we go from low to high. Okay, so here's that term again, or that long expression at the top. Here are all the terms in the legend here. So we're going to take both configurations, and we're going to look at a low and a high Stokes number in each. Okay, so here's a zero flux case for low Stokes number. And not surprisingly, what we see is the Stokes settling velocity. So these are normalized by the settling velocity. So this is -1. So on the left hand, right, so particles are settling downwards according to their Stokes velocity at low Stokes number. And because we're maintaining a zero flux, this is enforced by the boundary conditions of the case, something else has to be offsetting this in order to get zero flux. And what that is this R4, which is the preferential sampling. So oddly, the particles are preferentially sampling the flow, but they're actually preferentially sampling upwards. And this is because something needs to balance. So they need to be resuspended by showing up in positive velocity fluctuations of the fluid to offset the downward settling flux. When you start to get a lot of inertia in the flow, you still see, again, this constant settling, right? That's the R5, that's this purple one here. But what you see is really now the primary contribution in the outer is this red line, R3, which is the turbophoresis. So due to the gradient of S, which I'm not showing here, you actually have an upwards turbophoretic drift, which is balancing the settling flux here in the outer layer. And in this inner layer, sort of below Z plus of 100, you actually have a contribution of turbophoretic drift going downwards now. It actually switches sign because the gradient of grad S, or of the gradient of S. And you actually have contributions from this yellow and this blue curve over here, which are the diffusive term and the preferential sampling term. So what you see is that out here, you actually have a balance between two terms, somewhat unlikely, but down here, you actually have contribution from several. If instead you look at the constant flux case, then you wind up, okay, in the low Stokes number, the very trivial result that the flux is just simply equal to the settling velocity, right? So this is just R5, and that's equal to the entire sum. If you look at this for high Stokes number, now what you see in the outer layer is, when I say outer layer, I mean Z plus of 100 or larger. You actually see something that looks like homogeneous isotropic turbulence, where the flux is actually being dominated by this tendency for particles to collect in downward regions of the flow. So this R4, this component right here, actually dominates the enhancement of the settling velocity. However, below Z plus of 100, you actually see, again, a significant contribution both from turbophoresis, which is also pointing in the negative direction, but you're also seeing this diffusive component, R2, which is this blue dashed line over here. In all cases, R1 and R6 are actually quite negligible. So the takeaway here, if nothing else, is that there are two sort of different regimes. In the outer layer, it sort of looks like homogeneous isotropic turbulence, but near the wall, you start to get contributions from other terms, which are unclosed. All right, and that's kind of how I'm going to finish up here. If we talk about future modeling perspectives. So that Rosa paper that I referred to has an expression that looks like this. And their goal is to say, all right, in isotropic turbulence, is there some sort of parameterization based on Stokes number, SV, Reynolds number, that describes this enhancement on the settling velocity? Now there's a lot more to worry about when you actually start considering wall-bounded turbulence. From the results from the DNS, we see that these two terms are negligible, the R1 and the R6. So, as expected, this artificial diffusion plays no role, which is good because that's artificial to begin with. This acceleration is negligible, and that's good. We have this sort of the constant term, right? The actual Stokes settling, that's constant, known. That's, of course, all fine and good. We have these two terms, the one due to diffusion and the one due to turbophoresis, which play a very active role, and they're unclosed. And so, in future modeling perspectives, you'd have to do something about these. This term here is also very important, this R4. This is this preferential sampling of the flow of the background fluid velocity, which happens when you start to get a preferential concentration. Bragg et al. And Richter in 2012 show that this term itself can be broken up into what's called an advective component as well as a diffusive component. And if you look at this, all of the efforts in isotropic homogeneous turbulence are actually only referring to this term. And so if you're going to extend this analysis, right, which is hard enough as it is, but if you're going to extend the analysis, especially to near wall cases, now you have to worry about two more terms as well as the diffusive component to this. And this is going to be the future of our ongoing work. So to summarize, we sort of set up a PDF-based theoretical formulation in order to study what controls this particle, the settling velocity of inertial particles in wall turbulence. The DNS shows an inertial enhancement, and so in the outer layer, it is behaving quasi-homogeneous, and so we see a lot of the same effects that you would see in homogeneous isotropic. In all cases, we're violating this Rouse law, which is actually expressing the concentration and how it relates to the flux. As I just said, yeah, in the outer layers, it behaves quasi-homogeneously. We see this preferential sampling. That R4, as I've been calling it, term is the most important. And near the wall, we see actually a balance between a lot of the different terms. So near the surface, the gradients of the concentration and the particle Reynolds stress add multiple unclosed terms, which would need to be accounted for if you're going to get a proper determination of how inertial particles are actually settling through wall turbulence. And again, as I noted before, I'll do it again, all of this matters even though the SV number is 10 to the minus 2 in this case, because we're using WS as the relevant scale, not the flow velocity. So this was just sort of a high-level overview, a lot more details, as well as an asymptotic analysis on some of these terms, right? So we measured them using DNS, but we also looked at various limits of Stokes number, SV number, as well as Z. These can be found in the archive paper, which you can go to this link here. It's also included in the material inside this directory. So thank you so much for watching. I hope you enjoyed.